All right, 10-3, we are learning about logarithms. Might be the first time you've ever heard the term logarithms. You probably see them on your calculator. Let's take a look at these calculators right here. They actually have the functions on the calculator. So right here, you'll see a log key, log. You've probably seen those for years. You'll see the ln, the natural log. On this calculator, does it have it? Yeah, it has a log right up here on the, right under the second key, and a natural log right there. The graphing calculators allow you to do more than just the basic logarithms. If you go into the math key here and you go up or down to letter A here where it says log base, you can actually do more complex logs in there. I do know that on the final there are logarithms, but you can't use a calculator. So today you're gonna have to learn how to do them without the calculator. So make sure you focus in on that and don't just focus on the calculator. But there are quite a bit of capabilities with these graphing calculators to be able to do these logarithms. So what is a logarithm? A logarithm is a power you have to raise a particular base to get a particular number. That's a lot of words. If I take a logarithm like this, you'll see log, that just means logarithm, doesn't mean anything other than the word. You have a base A, a C, and a B. So you have these three different numbers. If I were to just rearrange them into something you already know, it's this right over here. Logarithms are just reworked exponents. The A is still the base. The B here is what you're trying to find. And the C here is the exponent. All right, so I might say something like, if I have a base 2, what do I need to raise that base 2 in order to get a 32? How many times do I have to do it? Well, we might actually find that you have to raise it 5 times. You might just think, okay, well, how many times do I need to multiply 2 by to get there? So 2 times 2 times 2 times 2 times 2, that's 32. So I know that x is equal to 5. Or what I could do is rewrite this as a logarithm and say something like the log of base 2 to the 32, what does that come out to? It's the same question, it's just written in a more formative way. So what I'll do here is I'll go to my logarithm function here. I'll say base 2 and I'll say 32, and I bet you it comes out at 5. So logarithm just allows you to solve for that function. And we find out here that x here also equals 5. Now we could just kind of guess or think about what x could be here without the calculator, and that's what we did. But where logarithms become beautiful is if the exponent is not just a solid number. For example, what if I asked you, what do I need to raise the number 8 to get 492? What do I have to raise 8 to? Well, I might say, okay, 8 times 8 is 64, times 8 is 512. So it's not 3 eighths, it's not 2 eighths, it's a number in between the 2 eighths. It's a decimal. The exponent is a decimal. So how do we find that exponent? How do we find the number that I need to raise 8 to get 492? You guessed it, logarithms. So I'll go down here to my log function, and I will literally put log of base 8 and 492, and that will tell me what the x is. So we'll go base 8. We know it's between 2 and 3. We'll go 492, hit enter, and there it is, 2.98. So x here is 2.98, which means we need to raise 8 to that number in order to get 492. So it allows us to find the exponent. All right. So 2 to the x power equals 16. Or I could write this as 2 base 2 to the 16 equals x. Or how many times do I need to multiply x or 10 by to get 10,000? I could figure that out in a logarithmic format. If the log base is not specified, it automatically defaults to 10. So if I said something like, what is the log of 54? Or something like that, that really is, what is the log base 10 of 54? If it doesn't write it, then it automatically defaults to 10. All right, first thing we're going to do here is just rewrite the exponents. So we're going to write these logs as exponents and then these exponents as logs. So I'll do 2 of them of each, and then I'll have you guys do them. So this is 3 to the negative 4 is equal to 1 over 81. So the base always stays the same. The log base always stays the same. The 4 goes into the exponent spot equals 1 over 81. And this makes sense. If I have a negative exponent, it causes the 3 to the 4th power to go into the denominator. And to get an 81, it is 3 to the 4th power to get 81. All right, so next one here, base 4 to the 3rd power equals 64. If I'm going from exponent to logs, now we'll go log base 6 of 1/6 equals negative 1. Or log base 2 to the 32nd equals 2. All right, you guys do CD, CD. All right, this is 6 to the negative 2 power equals 1 over 36. This one here is 2 to the 5th power equals 32. For this one, this is log of 7 to the 1/7 equals negative 1. And then log base 3 of 81 equals 4. All right, now they're asking us to solve. Log base 3 of 81 equals x. I could certainly put this in our calculator, but I'm going to show you how to not use your calculator. So we would say that the 3 to the x power equals 81. How many times do I need to multiply 3 by itself to get 81? 4 times. And you could test it too.
3 times.
3 times 3 equals 9, times 3 equals 27, times 3 equals 81. Or 3 times 3 times 3 times 3, 4 of them equals 81. So in this case, x here equals 4. I'll have you do those up there. I'm going to do the fraction one next. This is 7 to the x power equals 1 over 49. Well, now we're dealing with an x that has to not only make 7 bigger, but it has to put the 7 into the denominator. So this is x equals -2. -2 will cause, the negative causes it to go down to the denominator, and the 2 causes the 7 to be squared. All right, you guys do B, C, E, and F. All right, 6 to the x power equals 216. How many 6s does it take to get to 216? It takes 3 of them. X equals 3. 6, 6, 6. Isn't that the sign of Nero? Is it Nero that 666 represents?
Yes.
Is it? Okay. All right. Sign of Nero. All right, this here is log. What's the base of this log since it's not specified? It's 10. So how many 10s does it take to get to 100? Just 2. All right, what do I need to raise 2 to get 1 over 32? -5? Yeah, the negative is what drops it into the denominator. It's the 5 that makes it go larger. All right, 4 to the x power equals 1 over 64. What do I need to do with x? -3. All right, let's look at these logarithms. It says evaluate the logarithms on your calculator. All right, so if you don't have a graphing calculator, you're probably not going to do well here on these. You'll have to watch some kind of YouTube video on how to use these calculators here, because these will only do base 10. Where it says log right here, this is only base 10. So you're going to go to the math key here. You're going to scroll up to the log one, and it allows you to change things around. So I'm going to go ahead and put a 6 here as the base, and I want to find that to be a 1. It's just asking you to do it in your calculator. You could just do it like you did in the previous one and just skip the calculator talk. The only time you won't be able to use your calculator is if they ever gave you an example of a non-perfect logarithm, like the first one I did where we were trying to find, you know, what do we raise the number 8 to in order to get to 400 and something. You'd have to use a calculator for that guy. So let's go again, enter. We'll switch this to a 1 and a 2. All right. Five. 1 divided by 25 is -2. And the last one here, we'll put a base 4. And then 1 over 1 divided by 64. You get -3. Okay? All right, a little bit of reviewing here on exponent rules. Just that a negative exponent is just saying move that puppy to the denominator. That's all the negative means. Anything to the 0 power is always 1, so keep that in mind. And b to the 1 is just b. Anything to the 1. The last concept, I just want to give you just enough information to move on to higher things related to logarithms, and that's the natural log and this E key. All right, the E, oftentimes you'll see on a calculator right here. Here's the E. Have you guys seen an E before on there and wondered what it was? Well, I'm going to tell you today. The E is just a common base. There is a base that's super common, almost as common as 10. Some regards more common than 10, maybe not. But the base is 2.71 and it's some change. In fact, I think, let's see if I just put E here and see what we get. E. It's actually a bigger number. So I did in my calculator, E to the 1. It's actually 2.71828182, and it continues to go on forever without ever repeating. And it is essentially like a pi type of number, 3.14159. This is just as popular as pi. It's a number that forms naturally, which is why we call it a natural log. It comes out of nature. Here's where the number comes from. Do you remember last time where we had a equals 1 plus r over n to the nt power? Do you remember that formula? Well, the n was the number of times something compounded. And the biggest that we ever did with n was like if it compounded daily. And if we compounded it daily, it was 365. But what would the number be if I wanted to compound it hourly? Well, 365 times 24. That would change this to hourly. Well, what happens if I wanted to have it compound per minute? Well, you could make that calculation. What if I said per second? What if I said per nanosecond, half second, millisecond? And then what if I just said, I want this to be in a constant state of compounding, basically infinity. If n becomes infinity, then this part right here becomes 2.71 and some change, naturally. So as you compound to infinity, you get the natural logarithm. And this is important if you go into like any kind of finance industry. You want to be a tax person, you want to learn about finance, you want to go into anything related to money. This is going to be your best friend. What does money do when it's compounded at a given base? And that is 2.71. Happens naturally. All right, so that's the natural log. Since e is so common, rather than using log e of x, we just use the common function called ln x, and that's just natural log. Natural log of x. Does that make sense where that number came from? The final thing they want you to do is just do these on your calculator. You could do it on your regular calculator as well. We'll go natural log of 29.6. What did I do? 29, oh, I put a plus sign, delete. All right. 3.387. Natural log of 3 divided by 7 equals negative 0.847. And then finally, natural log of 20.6.